Hi everybody. Today I'm talking about wheel design and how your wheel size impacts the strength of your wheel, and specifically in this video the barrel strength on the inside of the wheel, how the size of your wheel impacts the strength uh, characteristics of your wheel. I will do here simulations from 16-inch to 22-inch size wheels and jumping 2-inch sizes higher each time. And here you can see some of the calculations I have done, but let's go deeper. Next slide. So how I have modeled this, the actual barrel shape in this wheel is similar than in Avu's MC04 or something like that. It's an 8 times 18-inch wheel, and there the barrel thickness here is about 4.8 millimeter. And how I've done the FEM simulation, the material is A356 or something like casting aluminum T6 heat treated. I have made here then on the inside edge 150 millimeter wide area, and there you press it with 15,000 newtons force. And I haven't modeled in this versions the spokes because it's irrelevant to know which barrel is strongest, because in theory they act the same way. In real life, the forces that are generated on the barrel is a little bit higher because it's also flexing a little bit here, and more movement means more stress. Do notice that I have here on the inside pretty solid sturdy lip, which is good for driving characteristics. So if you want a very precise turning wheel, you need to have a lot of material there. It also helps a lot with the FEM calculation strength and making it much stiffer. So the base wheel, 8 times 18, the barrel weight is 5.29 kilos, and that's the reference size. At the moment, I cannot see what the actual number here is because I'm using my laptop. I think it was 157 megapascals, and I think it flexed 0.8 millimeter, and the safety margin is 1.1. So it's holding that force there, and there's no problems with this wheel. Then the next size is the 16-inch. I'm keeping the same 8-inch wide width on these wheels first to see how it impacts if I just change the diameter. So 8 times 16 is 4.69 kilos. It's 13% lighter and 3% stronger. So it goes to 160 megapascal or something like that. 0.1 millimeter less flex, so 0.7 millimeters. And safety margin still 1.1. Sadly, the Autodesk Fusion, which I use for this simulation, it doesn't show the decimals, only one decimal here, so it's a little bit stronger, but it shows just one decimal. Then let's go to bigger size, 8-inch times 20. Weight jumps to 5.89 kilos. It's 11% heavier and about 6% weaker than the 8 times 18-inch wheel. And now, is it 166 or something like that? The stress here on the barrel, and same 0.8 millimeter or 0.9. I cannot see again. How to get this? Cannot get it small. Safety factor is now minimum 1.1, so it still holds, but it's starting to get too weak. Let's jump to 22-inch size. Barrel weighs 6.49 kilos. It's 23% heavier and 8% weaker than 8 times 18. And now the forces go to 170 megapascal area, 168 or what is it? and it flexes 0.9 millimeter. Safety margin still shows it's 1, so it should hold, but it starts to go fast to the wrong direction. But now you start to wonder why I'm simulating 8-inch wide wheels all the time, because if you go bigger in size diameter, you usually go also wider. And what about the typical wheel size for each diameter? For 16 inch, it's 6.5 times 16, and that 8 times 18 is the world's most popular size. So that's the stock. This 20-inch size, the width could have been 8.5 inch, but 9-inch was pretty close to same numbers. So I'm going for the 9 because it's easier. You have 8, 9, and 10. For the 22-inch, 10-inch wide is the most popular width in that size. And how does it then impact for the strength requirement? Actually, quite a lot. The reference wheel 5.29 kilos. If you go to 6.5 times 16, it's 4.14 kilos. It's 28% lighter and 5% stronger. Not a huge jump, but yeah, of course, smaller wheels are lighter and stronger. That comes because the curvature of the wheel, when it comes when it's tighter, it's strong, but when it comes bigger, it's starting to be almost like a flat, and that's why it bends easier and flexes easier. That's where the differences mainly come from. So if you have 22-inch wheel, the diameter is so big and it's almost flat on the test area. Okay, if the wheel size is 9.20 inch, it's 6.36 kilos. It's already 20% heavier than 8 times 18 and 8% weaker. Safety margin is still 1, so it should hold, but it depends, of course, on the stress levels. But let's go to 10 by 22, and there we can see weight has jumped to 7.56 kilos, which is 43% heavier wheel for the barrel. It's pretty much similar size. Also, if you go to higher wheels, they will be much heavier. But it's now 23% weaker. And now the safety factor is 0.9, so it's not strong enough anymore. And the maximum stress, is it 180 megapascals or something like that? And the flex is now 1.1 millimeter. And the 18-inch wheel, it was like 0.8 millimeters, so much less. How about the actual stresses then? Because if you put a bigger wheel, you need to have same tire outside diameter, and here are similar tire outside diameters for each wheels. For the 16-inch size, you have two 1570 16-inch tire. The sidewall profile is that 70 from 250. It's about 150 millimeters. For 8 times 18, it's 21560 18-inch size, and sidewall height is 129 millimeters. Still quite a lot flexing for the rubber. But when you go to 20-inch, which is actually this 255/40 R20, that's the Model Y wheel size if you want to go one size up. And there you only have 102 millimeters left. What does this sidewall difference means? I have calculated here how much more stresses these side profile changes create for the wheels and tires and suspension, bearings, everything like that. And if somebody, I know there's people who are riding 22s in Model Y performance cars, and they have 265/30 R22 in the front and even wider tires mostly in the rear. There the sidewall height for the tire is only like 80 millimeter, and that's 60% more stresses for your suspension components and wheels, bearings, and stuff like that. This is one way to look what's the impact is for your car if you go to bigger size wheels. If somebody is now having that 16-inch size wheel, I guess they probably won't even think going to 20-inch size wheels because there's no sense. It's so much worse ride quality and everything goes to worse. But if you already have big wheels in your cars, think about going smaller. It helps in many things. Other way to look at this is the uh, what's the uh, area that you're pushing against the road. What's the shape and size of that area in each tires? And there's a separate video already in YouTube which I made a long time ago where I making comparisons based on original Tesla 255 wide tire and narrower tires. What's the impact for the softness for the ride? 255 wide tire flexes about 10 millimeter on certain force, and 215 millimeter wide tire flexes almost 18-20 millimeter, if I remember correctly. So wide tire 255 versus 215 is 42% harder in small movements. So if you have a little bit shakiness there on the road, the wide tire is much more harsh for the suspension again, and it needs to do more work, and it creates more stresses for the wheels, bearings, joints, and stuff like that. In Model Y, everybody knows that the rear struts are not super strong, and usually they are changed before the warranty is out on warranty, and after that you need to replace them every 80,000 kilometers or so, or even less if you have very big wheels and tires. This impacts directly to that how much stresses you actually are delivering for your suspension components. So that was just talk. Let's use some actual calculations here and see what the forces can actually be. So if you're running low profile tires, that's a fact, you will have more stresses for your suspension, and here I have tried to evaluate them. The 8x18 wheel weight is 5.29 kilos. If you go to 20-inch size wheel, 9x20, that's 6.36 kilos. It's 20% heavier already, but it's 8% weaker based on my FEM calculations. And it will deliver 26% more stresses for your suspension based on the previous slide. So I just sum here roughly these together, and I think I will need 34% more material for the barrel to be strong enough. That means it will be 8.5 kilo barrel, which is 61% heavier than the 8x18 barrel. That's a lot already. But when you go 22-inch and 10-inch wide wheel, that was 7.56 kilos. It was 23% weaker on the first FEM simulation. The wide tires will create at least 60% more stresses for the suspension components with that. You sum those again together, you get 83% more material is needed for the wheel barrel, which was 4.8 millimeter to start with. And if you calculate that together, you get that the wheel should weigh 13.8 kilos, which is 161% heavier barrel than the 8x80. And that sounds very heavy. In real life, 8x18 wheel can be as about 13 kilos if the load rating is 930 kilos in your wheels. If you're going for 10 times 22 inch, similar looking wheels, spoke design, everything, and there the weight is 18 kilos with heavier load rating, so which means it should be little bit even lighter if the load rating is same 930 kilos. It's difficult to find wheels when they go that big that are with very low load rating. That difference is only 38%. And based on my calculation, which you see here, that should be 161% heavier. So that's way off. And now next slide, I will run some FEM simulations to find closer values and go there closer what the actual strength requirements are. Here, yes, your suspension takes some of that beating when you drive a pothole, but how it actually works is that first you have the rubber hits the pothole, then rubber flexes, it delivers the forces for the wheel, and after that the wheel delivers the forces for the suspension. So everything is first flexed on the wheel and tire, so the highest stresses come for the wheel and of course for the tire as well. And depending how much side profile your tire has to flex, it might be enough or it might be too little. If the pothole is too deep and you have only 80 millimeter rubber there and pothole is 80 millimeter, you will hit your curb, and usually what that happens, your wheel is most likely bent if you're driving fast and you hit a big pothole. So let's calculate again more. To start with, the barrel thickness was 4.8 millimeter. Now it has been jumped to 7.2 millimeter. The wheel weighs 10.4 kilos, 96% heavier than the 8x18. It's 2% weaker. And here I have only the same force that was in the first simulation, so 15,000 newtons. In real life, the wheel comparison 8x18, 10x22, 38% if in the wheel weight difference. And based on this simulation, you should have 96% heavier wheels, and that's not the case. And then you wonder why your 21-inch Uber turbine wheels don't last if you're running those 255/35s R21s in your Tesla Model Y or any heavy car that has this kind of wheels. And actually the weight of the car, it's not so big impact. The biggest impact is how fast you drive to that pothole. So here again the reference. On the previous slide you saw the forces which were there. They were in the same level. Flex was actually the same, 0.8 if I remember correctly, and safety margin was around that 1, so it will hold. But let's look then, if we bump the force from 15,000 Newton meters to 18,500 Newton meters force, in my estimation, that force should have been that 161% higher, which would mean 24,000 newtons force for the wheel, but that's too much. It would be like a tank wheel, solid wheel almost. So 10 times 22, 8.7 millimeter is now the thickness of the barrel, and the wheel weighs 13.3 kilos, and it's now 151% heavier, and still 1% weaker than the 8x18 wheel. Here you can see the stress levels are about 160 megapascal. It flexes a little bit less, and 0.7 millimeter, and safety is now the 1, so it holds. What you can take from this video is that the official strength requirement tests for wheels are pretty easy to pass. The real life situation and forces for the wheels are much harder if you are running a low profile tires. If you have side profile height in your tire less than 110 millimeters, and you hit a pothole which is 50 to 80 millimeter deep, which is quite easy to find. Will it hit the curb, or will there be enough tire for flexing So only the rubber is touching the pothole edges. And then if there is enough rubber, then it will be the strength of your wheel based on my simulation, which you have done here. If the wheel outer edge hits the curb, then the situation is very rapid and it will hit much harder on the outside edge of your wheel, and that will crack the wheel even faster. But the side profile height is not everything. If you have super wide tires and you need to use super high tire pressures like 3.9, 2.9 to 3 pars or 3.1 pars, it's still pretty hard tire. You have a lot of width in the tire, but if you have a lot of pressure in the tire, it's very strong. It's not flexing so easily. So that can create also a lot of stresses. If you have a narrow tire and you have the same 3 par pressure, it will flex 2 times more easier than the super wide tire. That I think comes from physical facts, and that's how it is. And if you have those low profile tires like 45, 40, even 30, you're tempted to put more pressure in your tire so it will protect your rims, and that will actually create more stresses for your wheels and rims, because then the tire doesn't flex at all. It just directly transfers the impacts to your wheel, and that will create it, destroy it much faster than riding with recommended tire pressures. One of the reasons I started to make this last week's simulation was that people told me that Volkswagen Pretoria Golf R 19-inch stock wheels are very weak. They bend very easily. And there the tire profile is it 235, 35, 19 or something like that. So there's practically almost any rubber there. And when you hit some speed bumps even, you can start to bend them if you drive fast enough for speed bumps. It doesn't even need to be a pothole. So why I'm making these videos on the YouTube on the wheel and design and strength and everything like that, it's because I'm designing my own wheels and tires at the moment, and I have been doing a lot of testing the last 2 years and designing one of the lightest and strongest wheels there is at the moment. Uh, at the moment, it looks like it will be 50% lighter on selected material, which means better handling, safer driving, and it will be 50% about cheaper to manufacture than normal casted aluminum wheels, because it will be manufactured by magnesium thixomolding, so high pressure injected casted wheels, which has been not possible before this because there hasn't been big enough machines to do it. And this is different from normal giga castings, so that the material which we are using is in a butter-like form, and that's make it possible so you can pressurely inject into the mold much faster, or in this case slower, that you don't get gases inside the mold, and which makes the wheel stronger, and that's make it possible to design much lighter wheel. It will be about 50% cheaper to ship because the wheels are lighter, so you don't ship so much weight around the world. Here comes the good things why it's EV wheel. It will be about 10% more energy efficient than current wheels and tires, which you at the moment have, especially for the Model Y. We have already measured 10% gains with our wheels and tire prototypes, and the current estimates are that it should be 13 to 15% more efficient when we get the actual wheels and actual tires we are designing at the moment, because it will take things to the next level. What's also interesting is that there is coming 2026 new CO2 regulations for wheels and other parts, where the CO2 manufacturing emissions also impact how expensive your products will be to sell. And here estimated reduction is 50% less CO2, which should be at least that. It's probably much more. But the biggest selling point will be huge noise reduction inside the car. And if you have been test driving new Tesla Model Y, the noise reduction inside the car is quite nice. Here the impact should be even higher than if you compare old version Model Y to new Model Y version, where they have lowered the noises inside the car, and similar impact in Tesla Model 3. And it will have wheel covers, just like Tesla has. Here you can see the wheel cover for my wheel. I cannot show yet how the actual wheel is looking, but hopefully I can do it in the next few months. And then you can see why it will be according to those specifications you saw here. If you are interested in this wheel, spread the word all over the internet and let people know this is coming for you. Here you can see some of the projects and products I have designed so far. And if you watch this long video up to here, you're probably interested in this stuff a little bit. If you need help, any help in engineering projects where you need to take things to next level, invent new products, invent new solutions, I'm usually pretty good at those. And thanks for watching, and keep tuning your cars.